I am not indeed from the Instituto de Astrofísica de Canárias. It's another Instituto de Astrofísica in Portugal, in Porto. But indeed, I am currently in the Canary Islands, so that's okay. my name is João Faria. It's really a pleasure to be here to talk to you a little bit about kima and how I've been using it to detect exoplanets in radio velocities. I just wanted to thank the organizers for giving me this opportunity today. So first of all, kima is not an acronym. It's actually the name of a passion fruit flavored drink from the Azores Islands in Portugal. When I went to the Azores, I tried this juice and I loved it, and I decided to use it for the name of my code. And the idea behind kima is that we want to turn radio velocity observations of stars somehow go through a machine, which I don't want it to be a black box, but still a machine that turns into planet detections. So the way that why is this difficult? Indeed, we've been doing this for several years now. The reason, or one of the reasons, that this is difficult to do in radio velocities is that the contribution from stellar activity from the stars themselves, it's several orders of magnitude or few orders of magnitude larger than the signals we are searching for. And you see here for our own sun, how the stellar activity, what the sun is doing in radio velocities compares to the signal that we are trying to find of the Earth. So that's the challenge, and why we still need to be working on this. Then for the model that kima implements, kima is basically a package that implements a radio velocity or a series of radio velocity models. We modeled a radio velocity time series with basically two components, one that is due to planets and another that is due to stellar activity. This has become fairly standard over the last years in the literature and in the community. One defining feature is that we use a particular version of the nested sampling algorithm called diffusive nested sampling, which is particularly amenable to exploring very multimodal and quite complicated posterior distributions. And that helps in making this algorithm and the package robust. Then there's another defining feature here. So as you see here in this sort of scheme that I'm showing, each of the parameters that we are interested in, whether it's for the planets or for stellar activity, has their own prior and their own posterior in the Bayesian framework. But kima also makes the number of planets, the actual number of Keplerian functions that we are modeling the data with, a free parameter itself. And so this parameter also is assigned a prior distribution, and from the data, information gathered from the data, we can estimate its posterior. So in a sense, we are sort of doing model comparison on the fly, or it's a reinterpretation of doing model comparison, because instead of having to test models with 0, 1, 2, n planets, we are doing this in one go. So we set the prior that sets our state of knowledge about the number of planets in a given data set, which can be no knowledge, and so a uniform prior, and then we get the posterior for this parameter together with all the others, all the other parameters. At the same time, I've been using stellar activity models based on Gaussian processes. You see here a description of the parameters involved in that. And some of these parameters provide constraints on the star itself. And so like some of these parameters we can then connect to the rotation period or to the evolution timescales of the active regions at the surface of the star. So you see here what a typical analysis looks like. We in the data space, and then in the posterior for the number of planets, and in the posterior for the orbital periods. What kima does is it tries a number of different solutions and tries to characterize the posterior for these parameters all together. And so in this case, very simple example case, but we get the detection of the two signals, a clear detection of the two signals, and we get information about the orbital periods and other orbital parameters. So going to a bit in practice, kima is written in a C++. That was sort of a decision that I had to debate because C++ is somewhat of a complicated language sometimes, and but the idea is that we are using C++ for that extra bit of performance. But then I also created a wrapper of some sorts in Python that makes it easy to run these models and to analyze the results more easily. So it's very easy to install and use kima. Just clone the repository, and everything should be fairly simple. And then what we typically do is we define the model in this file, in this C++ file, as you see here. I went to some length in order to provide a set of default priors that make the model robust, in the sense that you can use it for almost a large number of radio velocity data sets, but then can be refined with prior information. Then you can run the model, and importantly, you can analyze the results while the model is running, so that we can sort of this fail-fast approach, in the sense that we can see if things are working before we spend too much time on some of these analyses. Then I wanted to just go over a couple of highlights, late highlights of results that have used kima in the literature over the last few years. So you might have seen our result with Espresso, that we detected a very short period, very low mass planet orbiting Proxima Centauri. Here I'm showing you the analysis, we did the analysis of the radial velocities together with the full EFOF maximum of the CCF here, which is used here as an activity indicator, and all of this work was done within kima and using the model that I showed you before, with the number of parameters being the number of planets being a free parameter. And we're talking about a planet with a quarter the mass of the Earth and with an amplitude of just below 40 centimeters per second that Espresso allowed us to detect. Just another example, the even more recent detection of a circumbinary planet discovered in radial velocities. Here also, kima was used to estimate the posterior distribution for all these parameters and to do the radial velocity analysis, in the excellent work by Matthew Standing. So it's a 65 Earth mass gas giant orbiting this eclipsing binary, and it's only so far the second multi-planet system that we know in a circumbinary planet. And you see here the posterior distribution for the binary signal, and then for this planet. Then finally, just a couple of words to say that please, we did publish a paper in JOS a few years ago, presenting the code. There's been some developments since then, but feel free to read the paper for a tiny bit more information. The code is available on GitHub. Feel free to submit any issues that if you use it and you find any problem. And one of the challenges has been to keep documentation up to date. I think that's always one of the big challenges in software development. But you can find some documentation in this website. And I will take any questions. Thank you.
Thank you, João.